Buongiorno, baddies. Welcome back to another video. Today's first question is the base of a 39-foot pole. So, 39-foot pole. And a 15-foot pole. Oh god, that is slanted. A 39-foot pole and a 15-foot pole, like approximately. Yeah. Are 45 feet apart, therefore, so it's on the same piece of ground. Like so. And they're 45 feet apart. And both poles are perpendicular to the ground, like the 90-degree angle. The ground is flat between the two poles, as flat as I can draw it. What is the length of the shortest rope that can be used to connect the top of the two poles? So, so you guys may or may not be able to tell right away, but if I here draw a silly little parallel line to our ground, or as good as I can, you'll see that you can connect these two tops like this. Well, yeah, as good as I can do it, okay, don't judge. As good as I can do it. You can connect these two tops like this to create, voila, a triangle. Wow. And since we know that this is 39 feet and this is 15 feet, that means that this little bit here is 24 feet because 39 minus 15. And this bit, as it's already told you, is 45. And since 24 and 45, let's see if we can make a pi-algorithm trio. A pi-algorithm trio is when you have a right triangle, and it's just like a couple that you should probably remember that can make a right triangle, basically. And as you guys can see here, 24 and 45, we can divide by 3. So if we divide by 3, we get 8, and then you divide by 3. So then you will get 15. That is one of the pi-algorithm trios, 8, 15, and 17. So the last one will be 17. And since we divided by 3 first, we need to go 17 times 3. So 21, 51. So the shortest rope that can be used to connect the tops of the two poles is equivalent to 51 feet. Moving on to problem number 2. Find the hypotenuse of a right triangle whose legs have lengths 49, 0, 0, 0, 49, and 63, 0, 0, 0, 63. And as you guys can see here, these are immensely large numbers. We're not going to square these to use a pi-algorithm triple. We can, once again, take out a number, or numbers, to make our job easier. You guys might not be able to see it at first glance, but both 49, 0, 0, 0, 49, and 63, 0, 0, 0, 63 are able to take out a 1, 4 zeros, and a 1. And how can we test that we have the right amount of zeros? If we multiply this by 49 or 63, whichever one you prefer, we'll get a 49, 0, 0, 0, 0 at first, 0, because of the 1. And then if we multiply 1 by 49 again, these two last ones will turn into 49. That is equivalent to what the problem gave us, therefore this is the right number of zeros. So now that we pull out that number, we're left with 49 and 63. However, we can go even further with these by splitting this into 7 and 9. So now we just got 49 plus 81. You guys can take a moment to solve this by yourself because we're squaring them, pi-algorithm triple. This is not one that is conventionally used because it's not an integer pi-algorithm triple. So 0, this is a 1, 13. And since 130 is not a perfect square, it does not have anything we can take out that makes a perfect square. It's just the square root of 130. But wait, we are not done there. Because just like in the previous problem, which is slightly more simple and not as big of a number, we have to add back in the number that we took out. So basically, our final answer is 7, 0, 0, 0, 0, 7, because we took out a 7, and we took out a 1, 0, 0, 0, 0, 1, 130 square root. So yeah, that's the end of this video. I hope you guys enjoyed, and I hope you guys learned something new, and I will see you all on the next one. Bye-bye.